We now get to the workhorse of all of our physics, Newton's second law. Newton's second law is incredibly powerful. However, we need the other laws, such as Newton's first law, to understand how to apply the second law. So let's read what it says. Newton's second law in mathematical form is written right here. It says that the acceleration of an object, A, is proportional to the net, that's what this sum means sum, of the external pushes and pulls, that is the forces, applied by some other object. So you sum up those external pushes and pulls. If you double these, you'll double the acceleration. If you triple these, you'll triple the acceleration. The proportionality constant is something called mass. Mass is a measure of inertia, the desire of an object to go in a straight line at constant speed. Now, what this says is that if you're attempting to push a big object, for instance like a freight train, you'll get very little acceleration because it has a huge mass. If you apply the same set of forces upon something less massive, like say a raisin, you'll get a much bigger acceleration. Had we plotted these, let's say it was a one-dimensional plot, where this was the x component of the force, and this was the x component of the acceleration, we would get a straight line. And the slope of that line is mass. So for a particular object, let's say this is the bug, we'd get that curve. But if we were to do it on a different object, we might find that we'd have to apply a much greater force to get the same acceleration. And maybe this is the slope is mass, but this is for a truck. So the mass is the proportionality constant, or the slope, of a force acceleration curve. All right? Now, this is an incredibly powerful law, but it has an awful lot of things you need to think carefully about. Let's start with the fact that these are vectors. This is a vector, and this is a vector, and this is a scalar. And this scalar is always a positive number. So that means that this arrow A, the acceleration, and this net external force point in the same direction. Another thing that we notice about this, only external forces, that is forces outside the particle, are important, not those that are on the inside. Now you might not actually think about that being, really all that amazing, but it is, and it's extremely important, and I'll come back and talk a little bit more about that in a second. Let's finish the discussion about mass. Mass, we know from experience, it takes a greater force to accelerate a raisin. Like I said, mass, that is this thing called inertia. And the measure of the desire to go in a straight line, when you measure it, if you talk about it as a property, the object wants to go in a straight line at constant speed, you call it inertia. When you want to say how much, you say it has 3 kilograms. Mass is a measure of that. Now, the reason we ended up with two terms for this thing was we didn't understand this very well. One way to measure mass, as I've just said, is to put this into a force acceleration graph and measure the slope. So that's one way in order to determine what the mass of an object is. Let's go back and finish up our discussion about external. So external forces. If you had a bridge, maybe it's attached like this, and this bridge has lots of members in it. Not indicating that this is anything of a nice design bridge, but just give me something that has a bunch of stuff connected. What the equation says is that if you want to understand the whole bridge's motion, not the motion of any of the individual parts, you do not have to consider what's going on inside. You only have to consider what's going on the outside. What's going on the outside? There is weight pulling down at each one of these members. There is a normal force pushing up here, 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 here. But what goes on in the inside, that you don't have to care about. Now there's a reason for that. It's called the third law that explains why that works. But something that may have many, many parts and would be extremely complicated with thousands of forces, it may be possible to explain the total motion of it completely by describing just what happens outside of it. The other thing to note, besides this external, is this vectors. When you write this equation, you may say, hey, I got one equation I can solve for one unknown. That's if it was a scalar equation. This equation actually is a series of equations. The first one says the sum of the forces in x is equal to the mass times how it accelerates in x. The sum of the forces in y is equal to mass times how it accelerates in y. So if we're looking for a two-dimensional problem, this one equation actually is two equations. One vector equation, two scalar equations. And you can use each one of these to solve for an unknown. So you can solve two unknowns, not one. Another thing is, if you've watched the thing on free body diagrams, then you'll know how we're going to actually use this to solve it. So let's consider a ball flying through the air. And there's the ball. I'm going to want to identify the forces acting on the ball. I have weight. I have no applied. I'm going to neglect any air resistance. I have no normal. It's not touching anything. I have no tension. There's no string. And as I said, I'm going to consider sliding friction. It's not got a surface of contact. So weight, applied, normal, tension, friction. I'm going to draw me a coordinate axis, x and y. And then once I've got my free body diagram down, I'm simply going to read this diagram to fill in the left-hand sides of Newton's second law. Coming here, I look up and I say, how many forces lie along x? Well, there are no arrows along x. So 0 is equal to mass times acceleration in x, or ax is 0 meters per second squared. Right, this is a projectile. An object falling or shot, for instance, across some sort of like that. So in the previous chapter we said there's no acceleration in x. This is how we know that. We can use Newton's second law to find us accelerations, and if those accelerations are constant, we can apply the kinematic equations from the previous set of chapters. We can also look in the y direction. In the y direction I see one arrow, W, and it's pointing in the minus W. So I'm sorry, it's in the minus y direction. So I put a minus and a W. Notice no arrow. I'm not talking about anymore it being a vector. I'm talking about the magnitude of it, and it gets a minus sign. So it's this long, and it goes in the minus y direction. These are scalars, not vectors over here. This is equal to MAY. But I know that W is mg. This is equal to MAY. The m's cancel. So the acceleration in y is minus g, minus 9.8 meters per second squared. Again, what we found with projectiles. But what's important is that Newton's second law can work on any problem at any time, not just on one you know the answer to. So we can use it if we can identify these forces, and if we've plotted with a known force, for instance, or something, and found the slope, so we've got this mass. Usually this is done doing something called a balance, where we use gravity as the force pulling on this object. So if we know M and we can find F, we can use this formula to calculate A. And if we know A, then we can use the A. If we plot it, get an acceleration time graph, and we can find delta V. Or maybe we know it's a constant, we can apply the kinematic equations. So we're stepping one level more complicated than we did in the previous chapter. We're now not told A, we have to find A. And that's what we use Newton's second law for. Okay, that covers this discussion about Newton's second law. Please read carefully about the idea of these vectors, about the fact that it's summing. If the sum is zero, even if there are forces, the object can go in a straight line at constant speed, and about the fact that only forces outside, that is, nothing about what goes in this ball's particles matter. Only the fact that the earth outside of it is pulling on it can affect the acceleration. Very, very deep concepts. You're going to have to spend a lot of time to truly understand the majesty and power of Newton's laws. There's a bunch of videos with lots of examples to help you achieve this goal.